When we have a logistic regression model, we're often very interested in the effect that a particular explanatory variable has on the probability of success. And so with this particular logistic regression model here, let's say that we're interested in the explanatory variable denoted as x of r. To understand the effect that x of r has on the probability of success, we're going to focus on beta sub r. So if this beta sub r is equal to 0, then notice 0 times x of r is equal to 0, so x of r disappears from our model. And so then we can say that x of r has no linear effect on the logit of pi. In other words, x of r doesn't have an effect on the probability of success. However, if beta sub r is greater than 0 or less than 0, then that says it has a positive or negative effect respectively. So for this particular reason then, we are going to be very interested in this particular hypothesis test. An alternative to the way to write then these hypotheses is to actually write out the models for HO and HA. So the alternative hypothesis model is exactly what we had above. The null hypothesis model is exactly the same, but notice there is no x of r that's in the model. Now, when one often writes the model and writes the hypotheses in this format, one often refers to the HA model as a full model and the HO model as a reduced model because it's smaller than the full model. So in this particular section, we're going to be looking at two different ways to perform this type of hypothesis test. The first way is through a Wald test. And so our Wald test statistic is going to be denoted by Z sub W, W for Wald. And it's simply going to be the estimated regression parameter. If you really wanted to, you could put a 0 there, a minus 0, divided by the square root of the estimated variance for that corresponding beta hat. And again, this is going to test, is beta sub r equal to 0 or not? Now, for a large sample, this statistic under the null hypothesis, meaning if the null hypothesis was true, has an approximate standard normal distribution to it. And so what that means in the grand context of what we do in hypothesis testing, if I were to draw out the standard normal distribution then, so of course it's going to be centered at 0, it's going to be symmetric about 0 as well if I could draw it that way. And let's say that alpha was 0.05. We could put two critical values on our distribution here. Again, this would be Z sub 0.975. This would be Z sub 0.025. The probability being between these two critical values for a standard normal distribution is 0.95. And on the tails, it's 0.025. And so in the grand scheme of things, when we do a hypothesis test, we're looking for, is there evidence against the null hypothesis if the null hypothesis was true? And so what that means is we look at a standard normal distribution in this particular case, and if my test statistic, let's say, fell like way out here in terms of the actual observed value, then that would be very unusual to have occur, because very little probability on that part of the distribution. So we would say reject HO. If instead my test statistic, its observed value fell right about there, well, that would seem reasonable to occur if indeed the null hypothesis was true. So in that particular case, we would say don't reject HO. Similarly, out here, oops, if I had a test statistic, that would be very unusual to occur. So we would say reject HO. One can then, of course, then find a p-value associated with the same idea. So instead of comparing critical values, we compute probabilities underneath the normal distribution curve there. Now, these Wald statistic p-values and the test statistic are automatically given to us by using the summary function with the resulting models fit from the GLM function. Now, one could actually perform this hypothesis test with more than one parameter at the same time. We are not going to talk about that here because, as you might imagine, since I use the word Wald, the Wald test does have some problems. It's not as good as doing a hypothesis test another way, in particular using a likelihood ratio test. So that's what we will concentrate on here. So previously we've seen the likelihood ratio test. The likelihood ratio itself, we usually use the Greek uppercase letter lambda, and this indicates in the numerator, or this is in the numerator, the maximum possible value the likelihood function could take on if HO is true. The denominator is the same thing, but we allow either HO or HA to be true. So if this lambda is close to 1, then that says that what happens under HO seems reasonable in comparison to if I don't make that restriction under HO. If, however, lambda is close to 0, then that says, uh-oh, my maximum possible value of this likelihood function is much, much less than I would have if I didn't have this null hypothesis with restriction. And so we use that along with -2 log transformation of lambda to make a judgment about, well, should we reject HO or we don't reject HO? So let's have the setup again. Here's our hypotheses. Here's the model without, let's say, x of r in it, meaning that beta r is equal to 0. This is my reduced model, my null hypothesis model. Suppose we estimate this model to some data set. We'll call the resulting parameter estimates, like beta hat 0, beta hat 1. We will not necessarily call them, but denote them with a superscript in parentheses 0 to indicate that this is under the HO or H0 model. Same thing with estimates of pi. We can denote it that way. Then my alternative hypothesis model does have x of r in it. We'll call those resulting estimators as what we see here. So notice I put an A there to say this is under the alternative hypothesis. Then what we can do is form our -2 log lambda statistic in a similar manner to what we've done before in less complicated situations. So we have -2 log, and then in terms of the null hypothesis, the maximum possible value of the likelihood function under the null hypothesis, we have, and let me see if I denoted that later. Yep. Suppose we put together all these beta hats under the null hypothesis model. We put them into a bold beta hat. If you're familiar with working with the mathematical concept of vectors, basically I'm forming a vector there. So the maximum possible value of that likelihood function under the null hypothesis is denoted by this here. The maximum possible value of the likelihood function under HO or HA is denoted by saying the likelihood function evaluated at beta hat superscript A, which again represents a vector of these beta hats under the alternative hypothesis model. Okay. So once I have this formulation here, I can do a little bit of algebra, and I get down to a -2 log lambda statistic that looks like this. Now, one reason why I did this is to help you see how this comparison is being made for the pi hat with a super 0 and a pi hat with a super A, with an A superscript. You can see that if these two values for pi hat are near each other, this value inside the parentheses is going to be close to 1. And what's the natural log of 1? Well, it's 0. So if these pi hats are close to one another, again, we're going to have the natural log of something that's about 1. And then that natural log is going to end up corresponding to about 0. And so therefore my test statistic itself will be small over the different I equal 1 to n. If instead that these pi hats are far apart, then this is going to cause then this log to be farther from 0, and this, in the end, I'm going to have a large test statistic. Now, this -2 log lambda, once again, can be approximated by a chi-square 1 distribution if the null hypothesis is true, and we have a large sample. And so what that says then is that large values of negative 2 log lambda lead to rejection of the null hypothesis. So corresponding to what I've already said before, remember how lambda, if it's close to 0 or 1, same concepts that we learned first of all when we first talked about likelihood ratio tests. This leads into negative 2 log lambda as well. So when should the null hypothesis be rejected? Well, for large values in negative 2 log lambda. And how do we define large? How about the 1 minus alpha quantile from a chi-square distribution with 1 degrees of freedom? How should we calculate then the p-value? Well, this goes into basic concepts that you would learn in intro stat course whenever you're faced with a hypothesis test. Again, we're looking for evidence against the null hypothesis. So when we have something that's unusual to occur, that should lead to a small p-value. In this particular case, then, we would take the probability that A, where let's say A has a chi-square 1 distribution, the probability that A is greater than whatever the observed value is of negative 2 log lambda, that's going to be my p-value. Now, one could also set up these hypotheses as well for more than one of these regression parameters, these betas, to be set equal to 0. And if that occurs, then the chi-square distribution that you're using has, let's say, q degrees of freedom, where q is the number of parameters set equal to 0 in the null hypothesis. Okay, so let's take a look at an example that applies this, again, with the place-kicking data that we've seen before. We're going to go back to using this model that has both change and distance in it. So let's go ahead and estimate this model. So again, I say change plus distance to indicate both of them. The plus means and, not I'm adding the change value to the distance value. Put the results into mod.fit2, then I summarize it using the summary function. So let's take a look at this output here. So here is beta hat 0, beta hat 1, beta hat 2. Notice here the standard error column, based upon what we've seen before, is the square root of the estimated variance of beta hat. In this case would be 2. Now, the z-value column corresponds to our Wald test statistic. So if I were to take negative 0.112889 divided by 0.00844, I get negative 13.37. If I use a standard normal distribution approximation to this to calculate 2 times the probability of standard normal random variable z is greater than the absolute value of negative 13.37, I would get a number that is very small, less than 2 times 10 to the negative 16th power. So what this says is that there's strong evidence to indicate that the beta corresponding to distance does not equal 0. In other words, there's sufficient evidence to indicate that distance has an important effect on the probability of success. Now note that this is also given that change is in the model, because think of what the null hypothesis model would be and the alternative hypothesis model. Let me just write this out. So this would be the alternative hypothesis model. The null hypothesis model, when we're testing distance, would be logit of pi is equal to beta 0 plus beta 1 times change. Okay? We can also do a hypothesis test with change as well. In this case, my test statistic is negative 2.3. Using the normal distribution approximation, I get a p-value of 0.02. So given that distance is in the model itself, there is, you could say, marginal evidence that the change variable is important because I have a somewhat low p-value. More formally, if we work with alpha 0.05, here are the corresponding steps you could say that one would take to do the hypothesis test. With a strict alpha 0.05, p-value is less than 0.05, so we would reject we would reject HO there. Now, I would prefer not to formally say, well, there is sufficient evidence to indicate change has an effect on the probability of success given that distance is in the model. I would prefer not to say that full statement there, because notice if I use alpha 0.01, I would reach a different conclusion. So rather, whenever you have a p-value that's small but not quite so small, it is preferable to word it something like this, as I did originally, that there's marginal evidence to indicate that the variable is important. Okay, what about likelihood ratio tests then? We're going to look at two main ways to do it. The first way uses what's called the ANOVA function. I'll explain why we use something called ANOVA here, even though we're not doing analysis of variance. I'll explain that reason later. Also notice here how I'm using a capital A with this function. We will next, after this function, look at another function that has exactly the same name but uses a lowercase a. So that's why it's important to differentiate between the two, because they do provide different results. So the capital A ANOVA function comes from the car package in R. This car package is not installed by default, so you would need to install that yourself. This package corresponds to a book called an R Companion to Applied Regression, and so car comes from the C, the A, and the R from the name. Okay, so after I install the package, I say library car, and then I say capital ANOVA. I put in my results from fitting my model. It's in the mod argument of ANOVA. And then say I want a likelihood ratio test by saying test equal quote LR end quote. And here we go. So for the change variable, so this would be HO beta 1 is equal to 0. HA beta 1 does not equal 0. That p-value for that test is 0.022. Notice the degrees of freedom there. Here's my -2 log lambda statistic. For distance, we get a very, very small p-value. Notice that these p-values are very similar to what we had for the Wald test. Why? It's because we had such a large sample size. That's why these results tend to agree. Now, in the stats package, which is installed by default in R, there's another function called ANOVA, where that has a lowercase a there, that performs some similar stuff, but not quite exactly the same. And so if I say little a ANOVA, first argument is object, and I put in the results from using the GLM function, my model fit in mod.fit2. To say that I want a likelihood ratio test, I say test equal chi-sq. Why? Well, because we use a chi-square distribution with the test to make a judgment. And this is what I get. So here's my -2 log lambda statistic for distance. Notice exactly the same as what we had before. Now, what is different is this right here. That's 24.277, but before we had 5.2. Well, why? The hypotheses that the little ANOVA function tests can be different than the ones for the capital ANOVA. Here's what's happening in this particular case. The tests corresponding to change actually test this. The null hypothesis model with no explanatory variables in the model versus a model that only has change. Notice that distance is not in the model. Then the second test that we saw for distance has change in the model for the null hypothesis, and the alternative hypothesis has both change and distance. And so what happens here, if I keep on going all the way back, the way that the little ANOVA function works, it takes into account the order that you put these variables and performs a set of, you could say, sequential hypothesis tests depending upon the order. So that's why we see change first with a smaller model, and then when we did the distance test, we automatically had change in the model itself. The capital ANOVA function, though, gives us what we want, which is this test corresponds to, given that distance is in the model, let's do a test for change. For the distance row, given that change is in the model, let's do a hypothesis test for distance. Rarely, if ever, is that sequential set of hypothesis tests actually of interest. That's why I introduced the capital ANOVA function first, because that's the one that we will primarily use. Unfortunately, the capital ANOVA function will not always be available to us in all situations beyond logistic regression that we will be interested in this course. So that's why it's important for me to introduce the little ANOVA function, and we'll talk about next how we can actually then get the hypothesis test that we want. Okay. So we can use the little ANOVA function in a slightly different way. Suppose we estimate a model that has only distance in it, and we put the results into an object called mod.fit.ho. That would be my, you could say, HO model if I want to test just the distance parameter. I'm sorry, if I want to test just the change parameter. And then I can use the ANOVA function like this, where I put my reduced model first in the ANOVA function, comma, I put my full model second, my alternative hypothesis model second, and then say test equal chi-sq again. And so the way now that R behaves is how we would want it to behave. It does a test for change alone. So notice this 5.2455 there. That's exactly the same -2 log lambda statistic that we've seen before with the capital ANOVA function when we were performing a test for change. Okay. So why do you think then that the word ANOVA is being used here with these particular functions? Well, the little ANOVA function and the capital ANOVA function are both generic functions in R. They're set up to perform sets of hypothesis tests, just like what we did here, for a variety of different kinds of models. Now, for the prerequisite for this particular course in my book is that you would have seen analysis of variance before, what ANOVA stands for. In that particular setting, you're very interested in testing factors or explanatory variables to determine if they have an effect on the response variable. And the way you do that is you set up like an ANOVA table. You look at various sums of squares to help you perform the hypothesis tests. Here now, since we're using logistic regression, we don't have those sums of squares to look at. We don't have an ANOVA table to look at, but we're still interested in the same kinds of hypothesis tests. So that's how this name for this function continues to be used even in situations when you're not actually using analysis of variance. Okay. Now, something that I kind of skipped over is that in the output, you're going to see the word deviance appear a number of times. Let's actually look back. So, for example, we have something called resid.deviance, which stands actually for residual deviance. We have deviance listed right there. If I keep on going back, we're going to see more examples of deviance. Let's actually we'll go all the way back to the original output. So this is the summary output. We see something called the null deviance. We see something called the residual deviance. And so the purpose of this last set of notes then is to explain what the word deviance means. Okay. The word deviance is used in statistics to refer to the amount that a particular model, let's say, deviates from another model using our -2 log lambda statistic. So we're doing hypothesis testing. We're interested in how the null hypothesis essentially deviates from the alternative hypothesis model. We numerically measure this deviance with a -2 log lambda statistic so that we can perform a likelihood ratio test. Okay, so for example, when we are testing change, the -2 log lambda statistic could be referred to as a deviance statistic. There are two particular deviance statistics that you will often see in logistic regression model and other kinds of models output. The first type of deviance statistic is referred to as a residual deviance. And all this does, it gives us our -2 log lambda statistic for the following hypotheses. The null hypothesis model is your, let's say, the model of interest, what you're actually, let's say, fitting with the GLM model. So previously, we estimated the model with distance and change. So that could be our model of interest. Suppose that's our null hypothesis model for our hypothesis test. And what we can do is compare that model to a model that uses the observed proportion of successes for each observation instead. So in particular, if we had, let's say, binomial response data, we would use, let's say, the number of successes over the number of trials for a model that, let's say, looks at each unique combination of change and distance, similar to how previously we saw the estimating a model where we had number of successes out of a number of trials for a particular distance. So imagine you do exactly the same thing, but now we're looking at distance and change together for each unique combination of those. Simply use the observed proportion of successes as a way to estimate the probability of success. That would be the alternative hypothesis model. Equivalently, you can think of the alternative hypothesis model as this. Logit of pi sub j, where j is, let's say, the binomial format of our data, is equal to gamma of j. So notice I have a j here, I have a j there. And so what that means is for every row of my data set, or in other words, for every observation in my data set in terms of a binomial format, I'm going to estimate one parameter. Whenever you do that with a particular model, that model is often referred to as a saturated model because it has as many parameters as possible that one could estimate. You can't actually estimate each parameter. If you have a model that has, let's say, more parameters than the number of observations, you can't actually estimate each parameter then uniquely. So we typically would not want to do that. So the most number of parameters that we would want to have in a model is a model that has a parameter for every single observation. That's referred to as a saturated model. So with that terminology then, what the residual deviance gives us is our -2 log lambda statistic for the, let's say, model of interest versus the alternative hypothesis model, a saturated model. Now, I described what the saturated model is in terms of the binomial format of the data. You could do exactly the same thing with the Bernoulli format of the data as well. In that case, the observed proportion of successes for each, let's say, unique distance and change combination, that proportion would either be 0 or 1 every single time because you have Bernoulli data. Now, there's also something called the null deviance. And this gives us a -2 log lambda statistic as well, where the HO model is simply the logit of pi is equal to beta 0. So notice there are no explanatory variables in the model at all. And in fact, you just have this one parameter, beta 0. And in fact as well, you could easily find what that maximum likelihood estimate is without using a numerical iterative procedure. In fact, what it would be is beta hat 0 is equal to the log of the, let's say, pi hat over 1 minus pi hat, where pi hat represents the maximum likelihood estimate for a single binomial probability success parameter, what we had in chapter 1. That's it, where we had a homogeneous population. The null deviance, it has this as my HO model. The HA model is the saturated model. And it performs this particular hypothesis test in terms of the forming the negative 2 log lambda statistic. So just to show you where this occurs, here's my corresponding output. Let me do a little bit of erasing. Oops. I guess I'm erasing what I wanted to circle. For the model that has change in distance in it, the null deviance is 1013.4. This is my negative 2 log lambda statistic. 1424 degrees of freedom. Remember, we had 1425 observations. We're only estimating one parameter here. So that's why I have a degrees of freedom of 1424, because essentially I'm saying that that's how many parameters I'm restricting. The residual deviance, its negative 2 log lambda statistic, is 770.5. What that's doing is comparing the model that has change in distance in it to a model that has that uses the proportion of successes as the estimates for pi, or the saturated model, in other words. Notice there's 1422 degrees of freedom with this particular hypothesis test. Why? We are estimating 3 parameters, and we have a sample size of 1425. Okay. Let me get back. Okay. Now, these types of deviance statistics are often calculated as, you could say, an intermediate step for performing a likelihood ratio test to compare 2 models of interest. To give you an idea of how this works out, suppose we have the following hypotheses that we're interested in. A model that has just one explanatory variable as a null hypothesis model, and an alternative hypothesis model that has 3 explanatory variables. To help differentiate between the two, I'm going to put a superscript 0 or O and a superscript A with the corresponding parameters. Notice I do that with the pi's. Now, what the residual deviance for that null hypothesis model actually tests is our, you could say, the model of interest versus the saturated model. To form then the corresponding negative 2 log lambda statistic, this is what we would get. So this is exactly what we had seen before for the negative 2 log lambda statistic, but now I'm putting those particular pi hats in there. This is what it would look like with Bernoulli response data. Here's what it would look like with binomial response data. One little quick note here. Now you might be wondering, well, what happens if y sub I is equal to 0 or 1? What's going to happen? Well, if y sub I is equal to 0, notice how I have a 0 here. And by convention, 0 times anything, I don't care what it is always 0. So that's why that doesn't cause us a problem. Now, if we also look at the residual deviance then for this particular model of interest, then that becomes my null hypothesis model. My alternative hypothesis model is a saturated model. And I could form, once again, my negative 2 log lambda statistic with that. Now, if I were to take this model that's denoted by, let's say, equation 3, and then subtract from it equation 2, see if you can do that on your own, you will get this as your negative 2 log lambda statistic. And this is exactly what we had when I first introduced the negative 2 log lambda statistic earlier in this set of notes. So, get a residual deviance for one model, get a residual deviance for another model, subtract those 2 residual deviances, and you get the negative 2 log lambda statistic of interest to test in this particular case, whether or not two parameters are equal to 0. You will see this kind of use of these residual deviances in many different places. At least for what we're doing right now, the ANOVA function does a lot of the stuff that we need, but it's not always going to allow us to test, let's say, multiple regression parameters at the same time, or the parameters corresponding to multiple variables at the same time. And so one would need to resort to doing something like this. And this then essentially is how the little ANOVA function works in terms of the second way that I showed you how it did it. So this particular example, I want you to take a look at this example on your own. What this does, it tries to illustrate some of the concepts that I just was talking about, where I estimate a model here that has distance in it. This is my null hypothesis model. And then I have an alternative hypothesis model that has change. And so what I try to do in this particular case is I extract the residual deviance from the full model and the reduced model fits, so that I can perform this test essentially by hand. Or I shouldn't say by hand, but through using the actual necessary equations to do it. You can then verify based upon what we've done before with the little ANOVA function. And since we're only testing one parameter right now, you can also verify with what we did before with the capital ANOVA function to see that you end up getting the exact same results. If you remember, there's that statistic 5.245, the negative 2 log lambda statistic. Okay, so one last final comment. I showed you a number of different ways to perform a likelihood ratio test. What you should do in actual practice is use the way that is the easiest for the hypotheses of interest. So if you're only testing one variable at a time, the capital ANOVA function is going to be the easiest way to do it. Now, why did I show you these other ways? Well, at times you will need to do these other methods. Let's say if I wanted to test multiple variables at a time. So that's why we went through the process of doing this. Now, what we will find out later for some other regression models that we look at, it's not going to be as easy to do likelihood ratio tests because there are not functions like little ANOVA or capital ANOVA that are set up to work with those kinds of models. So with that then this ends this particular section on hypothesis tests for a regression parameter.